Welcome to the third topic of AQA GCSE Chemistry 9 to 1, titled Quantitative Chemistry. And the first thing we're going to start with is the law of conservation of mass. And it states that no atoms are lost or made during a chemical reaction, which means that the mass of the products always equals the mass of the reactants. So here I have an example. I have calcium chloride solution inside a test tube, which is inside a conical flask containing sodium sulfate solution. And this is stoppered, so nothing can escape and nothing can get in. And the mass at the beginning is 300.23 grams. And then we tip the conical flask over to enable the solutions to mix, and a reaction occurs. And we have a formation of calcium sulfate precipitate in sodium chloride solution. So what is the mass of the products? Well, if you said 300.23 grams, you of course are right, because the mass of the products must equal the mass of the reactants. Now this means that if an equation is balanced in terms of masses, then it also must be balanced in terms of the numbers of the atoms of each element on both sides of an equation. So if you have a look at the equation, we have one calcium ion and one calcium ion, but we have two chloride ions, but only one chloride ion there. So as a consequence, so that the mass is equal, we must have the same number of atoms. So therefore we'll need two lots of calcium ions. And on the left-hand side, we've got 2 moles of calcium ions, and on the right-hand side, we've also got 2 calcium ions now. So therefore that's balanced. One sulfur atom, 4 oxygen atoms, 4 oxygen atoms. So now, by putting the 2 in front of the sodium chloride, we have now a balanced reaction. Relative formula mass. The relative formula mass, or MR, of a compound is the sum of the relative atomic masses of the atoms in the numbers shown in the formula. For example, what is the relative formula mass of carbon dioxide? Well, the formula is 1 carbon and 2 oxygens. So therefore, the mass will be the sum of the relative atomic masses of each of the elements. So what do we have? We have 1 carbon with a mass of 12 and 2 oxygens with a mass of 16. So to work it out, we say 1 carbon and 2 oxygens, and the relative atomic mass of carbon is 12, and the relative atomic mass of oxygen is 16, times 2, because we've got 2 oxygen atoms, and you add those together, and we get a total of 44. Mass changes when a reactant or a product is a gas. Some reactions may appear to have a change in mass, but this is usually explained because a reactant or a product is a gas and its mass has not been taken into account. For example, if I have magnesium and it reacts with oxygen, the mass of the magnesium appears to increase. However, this is because oxygen is added to it and the oxygen has a mass. So therefore, if I had 24 grams of oxygen at the beginning, the mass will increase if fully reacted to 40 grams. This is because of the mass of the oxygen added to the magnesium. Some reactions have a decrease in mass because a gas is produced. For example, calcium carbonate can be firmly decomposed and carbon dioxide is produced. So at the beginning we would have a mass of 100 grams and after a mass of 56. And this is because carbon dioxide has escaped and 1 mole of carbon dioxide has a mass of 44 grams. Whenever you make measurements in chemistry, there's always an uncertainty about the result obtained. For example, when you measure a temperature or a volume or on a balance. And these can be 2 types of error. One human and one systematic due to the equipment. To reduce human error, we repeat the experiment many times. To reduce systematic, what we have to do is to use a more precise measuring device. So now you should be able to use multipliers, that's numbers in front of compounds, such as 2 times NaCl, in normal script before a formula and also in subscript within a formula, for example the 2 in H2O. You should also be able to explain any observed changes in mass in a non-enclosed system, for example the mass loss in thermal decomposition. And lastly, you should be able to represent the distribution of results and make estimations of uncertainty using a range of measurements. We're going to move on to talk about moles. Chemical amounts are measured in moles. The symbol for the unit of mole is MOL, pronounced mole. The mass of 1 mole of a substance in grams is equal to its relative formula mass. So let's explain that a little bit further. So 1 mole equals the mass divided by the mass of 1 mole. So for example, the mass of carbon dioxide will be the sum of the relative formula masses. So 44 divided by 44 would equal 1. We're going to use this formula triangle in a number of worked examples. So the first worked example we've got is copper. The question says, calculate the amount of moles of copper produced in this equipment. Okay, and the question has given us the molar mass of copper, or the formula mass, which is 63.5. So what we do is we want to know the moles, so we cover moles and we have mass divided by formula mass. So the amount is the mass divided by the formula mass, which is 1.27 divided by 63.5, and that equals 0.02 moles. Now, 1 mole of a substance contains the same amount of particles, atoms, molecules or ion as any other 1 mole of a substance. Now, the number of actual atoms, molecules or ions in a mole of a given substance is given by Avogadro. Avogadro's constant states that there is 6.02 times 10 to the 23 particles, atoms, molecules or ions per mole. Example here, a student decided to investigate the number of carbon atoms in a pencil lead. Pencil lead is actually made of graphite, which is an allotrope of carbon, so it's just made of carbon atoms. And he found that the pencil lead had a mass of 0.321 grams. And the question says, use Avogadro's constants, which will be given to you, you won't have to worry about remembering it, and calculate the number of carbon atoms in the student's pencil lead. So what we do is we say, fair enough, we want to know the amount of moles, so we need the mass given to us in the question, and we divide that by the relative formula mass, or in this case, because it's carbon atoms, the relative atomic mass. And what we do is we divide the mass given to us in the question, 0.21, and divide that by the relative atomic mass, which we can find in our periodic table, of 12, and we calculate that as 0.02675 moles. Now remember, the question wanted the actual number of carbon atoms. So to work that out, we need to times the amount in mole by Avogadro's constant. And that gives us the amount in mole, 0.02675 times by 6.022 times 10 to the power 23. And that actually gives us a very large number, 1.61 times 10 to the 22 carbon atoms. And we can actually use the amount of substance in equations. The masses of reactants and products can be calculated from balanced symbol equations. And chemical equations can be interpreted in terms of the number of moles. For example, when we say we have this balanced chemical equation here, what it actually means is that we have 1 mole of magnesium reacts with 2 moles of hydrochloric acid to make 1 mole of magnesium chloride and 1 mole of hydrogen gas. We've got another worked example here. It gives an example of the Solvay process where we have 2 moles of sodium chloride reacting with 1 mole of calcium carbonate to make 1 mole of sodium carbonate and 1 mole of calcium chloride. And it wants us to calculate the maximum mass of sodium carbonate that could be formed by reacting 40 kilograms of calcium carbonate with excess sodium chloride solution. Now, excess means that it will not be the limiting reagent. It means that we don't have to worry about how much of this we have, because the limiting reagent, the smallest amount we'll have, will be the calcium carbonate. So we'll actually have some leftover sodium chloride. And the question's also giving you the relative formula masses of both calcium carbonate and sodium carbonate to help you. So the best way to do this is to firstly work out the amount of calcium carbonate, and we work out amount in moles by dividing the mass by the formula mass. And we say formula mass here because this time we've got a formula. It's not atomic mass this time because we've actually got calcium ions and carbonate ions here. And what I've also done is I've converted the 40 kilograms to grams. So there's 1,000 grams in a kilogram, so 40 kilograms is 40,000 grams. And dividing that by its relative formula mass, which is 100 grams per mole. And that gives me a total of 400 moles of calcium carbonate. Now if you remember, if we look back at the equation, 1 mole of calcium carbonate reacts with 1 mole of sodium carbonate. So therefore, if I had 400 moles of calcium carbonate, it's possible to make 400 moles of sodium carbonate. So the amount of calcium carbonate is equal to the amount of sodium carbonate. So the amount of sodium carbonate is 400 moles. But the question wanted to know what the maximum mass of sodium carbonate was. So now I've got the number of moles, I've got the amount, and I've got the relative formula mass. To work out the mass, I have to times these two together. So I have amount times relative formula mass would be 400 times 106, which was given to me in the question, equals 42,400 grams, or 4.24 kilograms. Okay, so now you should be able to understand that a measurement in amounts in moles can apply to atoms, molecules, ions, electrons, formulae and equations. And for example, that in 1 mole of carbon, the number of atoms is the same as the number of molecules in 1 mole of carbon dioxide. You should be able to use relative formula mass of a substance to calculate the number of moles in a given mass of that substance and vice versa. And you should be able to calculate the masses of reactants and products from the balanced symbol equation and a mass given by a reactant or product. We're now going to look at using moles to balance equations. To balance the numbers in the chemical symbol equation can be calculated by the masses of reactants and products by converting the masses in grams to the amounts in moles and converting the number of moles to a simple whole number ratio. For example, if I had an experiment and I combined 3.1 grams of phosphorus and reacted with 24 grams of bromine to form phosphorus bromide, I could actually work out, using the simplest molar ratio, the formula of the reaction. So the best advice I can give here is to lay it out in a table format. So I want to compare how much phosphorus, the amount of phosphorus that reacted with bromine. The first thing I'm going to start with are the masses I have here. So I put in my masses of 3.1 and 24 as given to me by the question. And then I want to work out the amount. So I take the relative atomic mass of each and put that as they were given to me in the question. And then by dividing the mass by the formula mass, I can actually work out the amount. So 31 divided by 0.1 and 80 divided by 0.3 gives me a ratio of 0.1 to 0.3. However, this isn't the simplest whole number ratio, so to obtain the smallest whole number ratio, I divide by smallest number. 0.1 divided by 0.1 and 0.3 divided by 0.1 equals 1 to 3. Okay, the next concept we've already talked about is a limiting reagent. In a chemical reaction, 2 reactants, which is common to use an excess of one of them in excess, and the other one is called the limiting reagent because that limits the amount that you can actually produce. That limiting reagent is completely used up and therefore it limits the amount of products. I've got a worked example. Calculate the maximum mass of titanium that can be obtained from 500 tonnes of titanium chloride. And we've got a balanced equation provided. and we can see that 1 mole of titanium chloride reacts with 4 moles of sodium to make 1 mole of titanium and 4 moles of sodium chloride. Now actually what we're really interested in is, since the titanium chloride is the limiting reagent and it's titanium we need to find out about, don't really need to worry too much about the amount of sodium and sodium chloride. And I've laid out a table which looks at the relationship between titanium chloride and titanium. Now the first thing we've got is the mass of titanium chloride, which has been given to us in the question, which of course is 500 tonnes. Now 1 tonne equals 10 to the 6 grams, and I've put that there for you, and I'm just going to leave it like that, and you'll see why at the end. And we next have the relative formula mass of titanium chloride, and that's been given to us in the question, and that's 190 grams per mole. So using our formula triangle, we can work out the amount, and that is mass divided by formula mass, so 500 times 10 to the 6 divided by 190, and that gives us an answer of 2.63 times 10 to the 6. Now remember why we're doing this. The equation says that 1 mole is equal to 1 mole, but we don't know that we've got 1 mole. We've worked out we've actually got 2.63 times 10 to the 6, but the ratio is the same. So if I've got 1 mole makes 1 mole, 2.63 times 10 to the 6 will equal 2.6 times 10 to the 6. And then now we need to work backwards. So now I've got my amount and I've got the relative formula mass given to me by the question, you can see, of 48. What I need to do now is cover mass, and I'm left with amount times formula mass equals the mass. So 48 times 2.63 times 10 to the 6 equals 126 times 10 to the 6 grams, or as we know, a tonne is 1 times 10 to the 6 grams, so if we actually divide it by that, it will be 126 tonnes. I'm going to move on to talk about concentration, and we introduce another formula triangle. Many reactions in chemistry take place in solution, and the concentration of the solution can be either measured in mass per litre or mass per volume. For example, mass in grams divided by volumes in dm cubed, or commonly called outside the lab a litre. So we have a worked example here. If I've got 5 grams of sodium chloride is dissolved in 100 cm cubed of water, calculate the concentration by mass in grams per decimetre cubed. Now the first thing we need to do is actually change the volume of water to decimetres cubed. That's because in a question it's given us in centimetres cubed. So we know that 1 dm cubed equals 1,000 centimetres cubed, or 1 litre equals 1,000 millilitres. Okay, so therefore, if I've got 100 cm cubed, I would divide that by 1,000 and I would have 0.1 decimetre cubed. Now I've got the mass in grams as per the unit of concentration by mass, and the volume in decimetre cubed, and it simply is just as using our formula triangle to say cover concentration equals mass divided by volume. So we can say 5 grams divided by 0.1 equals 50 grams per decimetre cubed. More commonly in chemistry, we measure concentrations by amounts, measured in mole. And the amount of moles of a solute, or the mass in grams of a solute in a given volume, can be calculated from its concentration. And if the volumes of the two solutions that react completely are known, and the concentration of a solution is known, then the concentration of another solution can be calculated. If 15 grams of sodium chloride is dissolved in 200 centimetre cubes of water, calculate the concentration by amount in moles per decimetre cubed. So first we need to work out the number of moles of sodium chloride, and to do that you should know by now that we take the mass in grams and divide that by the relative formula mass in grams per mole. So that would be 15 grams as given in the question, divided by the relative formula mass, which is made of 23 for sodium, add 35.5 for the chloride ions, and we get an amount of 0.256 mole. And now we know the amount is 0.256, we know the amount. We need to divide this by the volume, We need to change the volume to decimeters by divided by 1,000, since 1 litre is 1,000 centimetres cubed. So the volume was 200 centimetres cubed, divided by 1,000 is 0.2 decimeters cubed. And now we can use the equation above, because we've got our amount in mole and our volume in decimeters cubed, and cover concentration is 0.256 divided by 0.2, and we have a concentration of 1.28 moles per decimeter. A new worked example where a student does a titration to find the concentration of a solution of hydrochloric acid, and the student titrates 25 cm cubed of hydrochloric acid with sodium hydroxide with a concentration of 0.2, and the equation shows that 1 mole of HCl reacts with 1 mole of sodium hydroxide, and the student had to add 28.6 centimetre cubed of sodium hydroxide. So what I've done is I've organised this information again into a simple table. So I've put my two volumes in and I've put my concentration of sodium hydroxide in. So the first thing I need to do is realise that if I've got 1 mole of sodium hydroxide, I've got 1 mole of hydrochloric acid. But I'm not sure how many moles I've got, so I need to calculate that first. So I take the volume in centimetres cubed, and I have to change that to decimeter cubed by dividing by 1,000, and then times that by the concentration, which is 0.2, and that gives me a concentration of an amount of 0.00572 moles. Now I know that the ratio is 1 to 1, so that gives me an equivalent amount of 0.00572 of HCl. Now I know I have the amount and I have the volume, I can work out the concentration. But remember, I have to change the volume again into decimeters. So it's what it will be the amount. So 0.00572 divided by 25 divided by 1,000, and that gives me a concentration of 0.229. Okay, so now you should be able to balance an equation given the masses of reactants and products, explain the effect of a limiting quantity of reactant on the amount of products. It is possible to obtain the amounts in moles and masses in grams, calculate the mass of a solute given volume of concentration in terms of mass per given volume of solution, and explain how the mass of a solute and the volume of a solution is related to the concentration. And lastly, explain how the concentration of the solution in moles per decimeter is related to the mass of solute and the volume of the solution. Now I'm going to talk about two kind of efficiency calculations we do in chemistry. One's percentage yield, and even though no atoms are gained and lost in a chemical reaction, most chemical reactions do not actually go to completion. And this is because the reaction doesn't finish, or it could be reversible. Some of the product may be lost when separated. Some of the reactants may react in different ways. You might get byproducts or side products. And finally, the amount of a product obtained is known as the yield when compared to the maximum theoretical amount as a percentage. So here's another worked example. A company calculated that we would produce 1.2 tonnes of magnesium, but actually only 0.9 tonnes was produced. Calculate the percentage yield. So the first thing we do is we write an expression from percentage yield being the actual yield divided by the theoretical yield, and then we times by 100 because it's a percentage. And then what we do is we plug in the values. So the actual yield in the question was 0.9, divide that by the theoretical yield, which was 1.2, and then we times that by 100, and we get a percentage of 75%. Another efficiency expression in chemistry is atom economy. Well, the atom economy, or also called atom utilisation, is a measure of the amount of starting materials that ends up as a useful product. So it's important for sustainable development and economic reasons that we use reactions with high atom economy to eliminate waste. And the percentage atom economy of a reaction is calculated using the following equation. So it's the sum of useful products or desired products of the MR divided by the MR of all products times 100. And again, I've got a worked example for you. In this reaction, the desired product is copper chloride, and the question's given us the relative formula masses of all of the reactants and products. It's asking us to calculate the percentage atom economy. So we write an expression for atom economy. So atom economy equals MR of useful products, in the blue, circle in blue, the copper chloride, divided by the MR of all products. So that will be the MR of the copper chloride plus the MR of water, and of course times by 100. So we end up with the 134.5 for copper chloride, divide that by the 152.5 of the copper chloride and water, times by 100, and gives us an atom economy of 88.2%, which isn't too bad. Now, finally, you should be able to calculate the percentage yield of a product from the actual yield of reaction and calculate the theoretical mass of a product given the mass of reactant and a balanced equation, calculate the atom economy of a reaction from to form a desired product, and explain why a reaction pathway chosen to produce specific products given appropriate data such as atom economy, yield rate, equilibrium position were useful of byproducts. The last thing in this topic is molar volume of a gas, and that is equal amounts of moles of gas occupy the same volume under the same conditions of temperature and pressure. Now the volume of 1 mole at room temperature and 1 atmospheric pressure is 24 litres, and we can use volumes of gases of reactants and products from balanced equations using the following formula triangle. So a mole of gas is equal to 24 dm cubed at room temperature and pressure. And lastly, I've got another worked example for you. The question says carbon dioxide was collected at room temperature and pressure. The volume of 1 mole of a gas at room temperature and pressure is 24. How many moles of carbon dioxide is 95 centimetres? And it asks us to give our answer to 3 significant figures. So remember, 1 mole equals 24 decimeters cubed, and we also know that relationship between decimeters and centimeters cubed is that 1 dm cubed equals 1,000 centimeters cubed. Therefore 24 decimeters will be 24,000 centimeters cubed at room temperature and pressure. Therefore, if I've got 95 centimeters cubed, I can divide that by 24,000, and that gives me an answer of 0.00396 mole. Okay, you should be able to calculate the volume of a gas at room temperature and pressure from its mass and relative formula mass, and calculate volumes of gaseous reactants and products from a balanced equation and a given volume of gaseous reactant or product.